What's the first thing everybody looks for following a hypothesis test and the most prevalent biostatistical concept you see in your medical literature? The infamous p-value. Now, any applied statistician has heard many times statements like, well, I just need one more p-value and I can publish my paper. Or, here's a list of statements I want to make. Could you give me the p-value for each one so then I can figure out what my results are? What is this magical p-value? Well, it's just a probability. A p-value is a measure of how much evidence you have against the null hypothesis. Remember, the null hypothesis is that the two treatment groups will have the same outcome. So I like this because it's a measure, meaning there's a continuum there, and in this case, if the value you get is small, then that means you have a lot of evidence against the null hypothesis. Whereas if the value tends to be larger, you have less evidence against the null hypothesis. But your measurement never tells you yes or no, the null hypothesis is true. Okay? And if two measurements are very close, such as 4.5% versus 5.5%, the measure you have is about the same. Now let's discuss this further by looking at our particular example. Okay, here's our preliminary results. In the standard treatment, we have 60% improved. In the new treatment, we had 76% improved. The question is, in the hypothesis test, is the observed difference we're seeing, 60% to 76%, so large that it gives us enough information that we do not believe in the target population the percent improvement would be the same regardless of the treatment. Okay? To do that, we do a hypothesis test, and since the data is percentages, and we're comparing two percentages, we know, of course, that the simple statistic we would use to do this test, that means without any other covariates involved or anything, would be the chi-square test. So we're going to put in the p-value, and the p-value for the chi-square is 0.015. Now remember, in the old days, we used to put in just significant or not significant. That's because we didn't have these computers on our desks, which would give us the exact p-value, so you had to look something up in a table. There's no reason to not put in the exact p-value today. So what does that tell me? Is there a difference between these two groups in terms of the percent improved? Well, if you presumed the two groups had the same percent improved, you would only see this much of a difference, or greater, 1.5% of the time. That's pretty small. So the amount of evidence we have against the null hypothesis is pretty large. Remember, the smaller the p-value, more evidence against the null hypothesis. Fine. So in this case, we'd probably say, hey, the new treatment seems to be doing better. Now, what if we have a sample size of 50 instead of 100? So I have the same 60%, but my sample size is now 50. I have my same 76% for the new treatment, but my sample size is now 50. So the estimates are the same, except the sample size is smaller. And remember, the larger the sample size, the more precisely you get your estimates. The smaller the sample size, the less precisely you get your estimates. That means you don't know as much. So that means you probably have less evidence for rejecting the null hypothesis. And in fact, the p-value from our hypothesis test gives us 0.086. So there's only 8.6% probability that we would have seen this much of a difference if, in fact, in the target population, the two treatments had the same percentage of improvement. Does this mean there's no difference? Because the p-value went from 1.5 to 8.6? No. It just means a p-value of 1.5% gives you more evidence against the null hypothesis than a p-value of 8.6%. It doesn't mean it's true or not true. Okay, so what are the important points we've talked about today? Well, there's nothing special about a p-value, it's just a probability. There's also nothing special about 5% for the significance level. In fact, I wonder if we should have any significance level at all. The sample size is crucial for determining your p-value. The greater the sample size, the more precise the estimates, the more likely you are to have evidence against the null hypothesis. And finally, we didn't mention this before, but if you've done the wrong statistical test, or if you've collected data and your two samples are not representative of the target population in a systematic way that is related to the outcome, then you have bias, in which case your p-value isn't very meaningful, is it? The p-value alone and the estimates don't tell you how much difference there is in the target population between the 2% improvements. For that, we need a confidence interval. And that is the subject of our next session.